I would like to introduce you to the first speaker, Florian Marquardt. I always try to pronounce it like a French name, and it's not. Marquardt. I probably mispronounced it. So he's a theoretical physicist with research mainly in the intersection between optics and nanomaterials. So this is optomechanics, really. And so that's really using a cavity containing light, interacting with a mechanical system, and using this interaction to control the mechanical system, cool it or control it in other ways. So that's what you're going to hear about in this talk. So Florian did his PhD at University of Basel in Switzerland. He then went and did a postdoc in the Swiss National Center for Competence and Research in Nanoscience, followed by coming to the US to work at Yale as a postdoctoral fellow, followed by a junior research group leader at the Ludwig-Maximilians University in Munich, LMU. And then, well, you can see he was pretty successful because he went directly to a full professor at Erlangen-Nuremberg. And from there, in 2016, he was selected as new director at the Max Planck Institute for the Science of Light in Erlangen in Germany. So he's begun to win prizes and things like that. Let me just point out that he won the Walter Schottky Prize in 2009 for the German Physical Society for groundbreaking research in the theory of optomechanical systems. And he's had I think a very competitive, I know these are very competitive, ERC starting grant from the Research Council from 2011 to 2016. So now we get to hear all about optomechanics.
Thank you very much, Paul. It's a pleasure and honor to be here, to be speaking at this symposium, and also already to be at the preceding workshop that took place at the Max Planck Center at the University of Ottawa in the preceding 2 days. So now in the next 45 minutes, I'll be telling you a story about coupling light to mechanical motion. And in order to start off, I'll go back into the history of physics. Now I guess every one of you knows Schrödinger's cat, which is a kind of metaphor that Schrödinger introduced back in 1935 to highlight some of the mysteries of quantum physics as he understood them. Yet, I'm also pretty confident that very few of you know that even 4 years before that, Schrödinger introduced something that you could call Schrödinger's mirror. So what was that? In 1931, Schrödinger wrote a letter to Sommerfeld, you know, the PhD advisor of Werner Heisenberg. And in this letter, he wrote the following: Dear Sommerfeld, in our seminar, we have debated for hours about the following case, which should be simple in principle. We measure to a high precision the momentum of a heavy mirror and simultaneously the position of a light quantum. Hence, the color of the light quantum and the position of the mirror are very uncertain. Here he applies Heisenberg's uncertainty principle. Afterwards, Schrödinger says, I let the light quantum be reflected from the mirror, like shown here. And so the mirror takes up twice the momentum of the light quantum because it absorbs the momentum and then kicks it back. After this has happened and after the light quantum has moved away, I have the choice to find out either the position or the color of the light quantum by performing a measurement on the mirror. So here he takes into account that this kick, this interaction, has suddenly correlated, or as we would now say, entangled the two objects, the microscopic light quantum and the macroscopic mirror. And so this letter is remarkable for several things. It already contains the elements of the argument that was later expanded by Einstein, Podolsky, and Rosen in 1935. And so it's no wonder that then immediately after this paper by Einstein, Podolsky, Rosen, Schrödinger was able to jump on it and actually explain it further and introduce the concept of entanglement. It's also really a precursor of Schrödinger's cat because it also already involves micro-macro entanglement between the light quantum and the mirror. And then finally, which is important for our story, it's the first instance of a discussion of this sort of the quantum entanglement that is brought about by radiation pressure, the quantum entanglement between light and mechanical motion. And so it's, so to speak, a very, very early example of quantum optomechanics. Now, in the following, I'll first give you an introduction to what we now call cavity optomechanics. Then I'll turn to, so to speak, one frontier of this field, which would be optomechanical arrays, where you couple many mechanical and optical modes together. Then there will be a brief interlude where I tell you something about topological transport in general, and then we'll apply that to photons and phonons propagating at the nanoscale. Now, radiation forces have played an important role in physics for quite some time. For example, even Arthur Eshkin in the 1970s already studied how to trap little glass spheres, for example, in the focus of a laser beam. And nowadays, this is important in biophysics in the form of optical tweezers to measure small forces. In addition, you can trap microscopic particles down to single atoms in so-called optical lattices, where you have standing waves of light. But in all these examples, usually the light field just provides external forces. The motion itself does not act back on the light field. It does not modify the light field pattern that you have here. And this will change when we turn to the field of cavity optomechanics. So now this is a cartoon of the paradigmatic system that we like to study in cavity optomechanics. In order to enhance the effects of the radiation forces, we use resonances. So first of all, we use mechanical resonances, for example, here this vibrating nanobeam. And we also use optical resonances here in the form of a Fabry-Perot cavity. The idea, of course, being that if you have an incoming laser intensity, it will be enhanced by a factor of, let's say, 1,000,000 or so, which would be the finesse of the cavity. And by the same amount, you enhance the radiation forces acting on this end mirror of the cavity. In addition, once there is some motion, this will automatically lead to a change in the length of this cavity. And as you know, this implies that the optical resonances frequencies shift around. So there's a very sensitive interplay, a very sensitive back action between light and mechanical motion. Now, I myself, I am a theoretician, so I want to describe the system, and I want to describe it in the simplest way possible to focus on the most important crucial degrees of freedom. And here they would be identified as, say, one mechanical normal mode of motion among the many normal modes that constitute this nanobeam. And then also one optical mode inside this cavity that would be typically the optical mode that is in resonance with the laser radiation. And so now if I write down the energy, that is fairly simple. I would say I count the number of photons and I multiply by h bar omega. So that would be the electromagnetic field energy. So that's written here. A dagger A is the number of photons and h bar omega the energy per photon. However, I just told you a moment ago that the optical resonance frequency itself starts to depend on the position of the mechanical mirror. And so that means we will get an effective shift of the optical resonance frequency, which is written down here. So the relative shift of frequency is given by x over L. X is the displacement, and L is the length of the cavity. So now here you see the basic cavity optomechanical interaction, which is the foundation for everything that I'll be telling you in the following. X, the motion, multiplies A dagger A, the photon number. You can also read it in another way. You can say, if my Hamiltonian, if my energy contains x times something, the something must have the dimensions of a force, and this force obviously is proportional to the photon number, and that is what you expect because this is nothing but the radiation pressure force. And then you add other terms. For example, you say, what about the mechanical vibration itself? To a very good degree of approximation, it will be described as a harmonic oscillator, and B dagger B would count the number of phonons of vibrational excitations. Omega, capital omega now would be the mechanical frequency that could be kilohertz or megahertz or gigahertz. Now, a short piece of experimental history. The very first experiments in the field of optomechanics date back a very long time to the pioneering work of Vladimir Braginsky, who later was interested very much in the precision measurement in LIGO. Here they had a macroscopic end mirror in a microwave cavity that was driven, and they were able to show that the mechanical properties of this mirror change depending on the irradiation with the microwaves. For example, you change the damping, the effective damping of the mirror. The first optical domain optomechanics experiment, again with macroscopic mirrors, of course, was performed in the group of Herbert Walter in the 1980s. But the modern era of optomechanics only started more recently when people switch to micromechanical structures, because as you go down to the micro domain or the nano domain, you can radically boost the effects. So now here's just an outline of the vast variety of different experimental setups that people have been exploring in this field. They range from literally mirrors glued on top of nanobeams over little disks where light runs around in a whispering gallery mode and then couples to the mechanical vibrations of the circumference, to photonic crystal devices which have the tightest mode volume and which will play an important role later in this talk. You can also replace the optical radiation by microwave radiation, which you would store, say, in an LC circuit on top of a superconducting chip. And then the mechanical motion in question would be the vibrations of this membrane that forms one part of a capacitor. Again, the vibrations will change the LC resonance, and this is exactly the type of physics that we have been talking about. So the largest optomechanical setup on the planet is actually these LIGO interferometers, because at the end of this interferometer you have a heavy mirror, and the idea is of course that you want to detect the motion of the mirror in order to detect the passage of gravitational waves. Nevertheless, it turns out the fundamental limits for the precision of these devices will be set by optomechanical effects when the unavoidable laser shot noise will produce a fluctuating radiation pressure force acting on the mirror, which leads to a kind of jitter that masks the signal that you wanted to detect. So in the next generation of devices, one is sure that these effects will play a role. Coming back to cavity optomechanics on smaller length scales, here's a short outline of the field as it has developed over the past years. So as I said, the modern era started around, say, 2006 with experiments on micromechanical structures, and then one of the goals was obviously to detect mechanical motion down to the precision ultimately limited by quantum mechanical effects, as well as to laser cool the mechanical motion down to the quantum ground state of motion. Once this was achieved, the field switched towards trying to build the first elements of a quantum toolbox to coherently control mechanical motion using the light field, and for example, leading up to optomechanical entanglement between mechanical motion and the radiation field, first achieved in microwave setups. If you ask me about the current situation or the future, I would say the field has expanded into several different branches, one important of which would be applications. And here I want to highlight wavelength conversion. The idea is that since a lot of successful quantum computation efforts are focused on chip-scale devices like superconducting qubits, you have quantum information typically in the form of gigahertz excitations stored on the chip. However, you want to transport them over long distances, and for that, as we all know, optical photons are really the carrier of choice. And so you want to have a coherent, reversible, high-fidelity process of interconversion between microwave photons and optical photons. So going from a microwave photon to an optical photon and all the way back with 100% efficiency. And there, these optomechanical systems are very promising because you can use the mechanics, so to speak, as an interface between microwave and optics. If you have a microwave cavity and an optical cavity coupling both to the same mechanical element. And right now, they are approaching 50% fidelity in such devices as shown here. So that's very promising. Then, more generally speaking, mechanics couples to all kinds of different quantum systems, so it can form an interface to hybrid quantum systems. What I myself am particularly interested in is optomechanics in unconventional systems, such as, for example, levitated drops of superfluid helium. There is a large area that deals with the foundations of quantum physics, where the idea would be that you use these radiation forces to control mechanical systems in such a way that you are able to form macroscopic superposition states, and then to test whether there are any new decoherence mechanisms that kick in particular for very massive objects. And so these systems here would be the largest mass objects to be put into superposition states where you can test these ideas. And then finally, and this is what I want to talk about, you can imagine that you put together many of these individual components into optomechanical circuits and arrays, and then you can study the transport and control the transport of photons and phonons. Now, before I go there, I want to tell you something about the most elementary physical process that can happen in these devices. So here's a cartoon picture of a typical situation. Imagine I am illuminating a cavity with a stream of laser photons, but as you can see, most of them are reflected, and the reason for that is that for this cartoon, I imagine that the laser is red-detuned from the optical resonance. So it is not in resonance, most of the photons are reflected. Nevertheless, let's imagine that for some reason there is already a photon inside the cavity. And then I claim what can happen is that the single photon gets converted coherently into a single phonon, that is a single vibrational excitation. This may sound a little bit odd at first sight, because if you think about the energy, this is of course 200 terahertz excitation, that may be a megahertz or a gigahertz excitation. But what goes on really is revealed if you also look at what happens outside the cavity, namely as the high energy photon is converted into the phonon, at the same time a slightly lower energy photon leaves the cavity. So what we have here is really a kind of coherent Raman process. Nevertheless, it's coherent in the way that it can happen back and forth several times. And so these are, if you want, Rabi oscillations converting a photon to a phonon. Now that's the cartoon picture. If I want to switch to the technical description, I would take the basic interaction Hamiltonian that I already discussed, A dagger A, the photon number, coupling to the displacement, here written in terms of B plus B dagger, the phonon operators. I would take this as a starting point. And now I have to tell you that usually G0, this coupling constant with the dimensions of a frequency, is rather small as compared to the photon decay rate. So you have to find ways to boost the effects. And you can do that in a very simple manner by just illuminating with a lot of laser power, which means you have a lot of photons. This term becomes very large. So, as is usual in cavity quantum electrodynamics, I can describe the situation by saying the light field inside the cavity, represented by this operator A, I can split into two terms. One is alpha, the classical complex amplitude that is set by the laser drive, and one would be delta A, the small quantum fluctuations around this large classical amplitude. So that's a standard scheme in cavity quantum electrodynamics. If I take this and insert that into the optomechanical interaction, I will get several terms, of course. And now I want to keep only the leading interesting term, and that would be the following. It is a quadratic Hamiltonian, because always you couple one delta A operator describing the quantum fluctuations of the light field with one B operator that describes the mechanical excitations. Not only is this a quadratic Hamiltonian, but also you understand that suddenly you multiply G0, the Bayer coupling constant that is set by geometry and so on, by alpha, which is set by the laser drive. So now you have a kind of tunable, enhanced interaction between photons and phonons. So G equals G0 times alpha would be the new coupling constant. And not only can you tune it and ramp it up by illuminating with a lot of laser power, but also, and this will be important, it's a complex number. It's a complex number for the simple reason that, of course, the laser drive has some phase, and so also the light field inside the cavity has a phase, so alpha is a complex number. Okay. So now this is already enough. This is really enough to understand, say, 80% or 90% of the experiments being done nowadays in cavity optomechanics. So you have one optical mode coupled to one mechanical mode, and you have a kind of tunable interaction between the two. That's enough to understand laser cooling or displacement sensing down to the limits provided by quantum mechanics. However, it is also quite obvious that you can go to much more interesting physics if you were to investigate situations in which several optical and mechanical modes talk to each other. For example, in this case, of a simple two-dimensional periodic array. Because then you can, for example, study transport of phonons or photons being engineered in a way by the light field. Now this is only a cartoon. Yellow is the mechanical mode. Optical modes are represented by blue circles. How does this look in real life? Well, this is the biggest optomechanical array to date that people have fabricated in the group of Misha Lipson. Here you see 7 optical disk resonators. Each of them can carry whispering gallery modes running around the circumference. They are coupled evanescently, so a photon from here can hop to the next disk resonator. And then finally, each of those can also vibrate. Simply the circumference can expand and shrink, and so that will interact with the photons. That's already pretty good. An even more promising platform are so-called optomechanical crystals. So what is this? Essentially, this is a kind of photonic crystal, which is at the same time a very good phononic crystal. So you have, for example, a two-dimensional structure of silicon. The dark areas are holes in the structure. In this case, they have the form of snowflakes. Turns out this is a photonic crystal. If you introduce deliberately a defect somewhere, like in the center of this picture, you can generate a localized optical mode that is trapped at a frequency inside the band gap of this photonic crystal. At the same time, this is also a phononic crystal, and at the same geometric defect, you get trapping of vibrations, so you get a localized mechanical mode. And then you have the usual optomechanical coupling, simply in the sense that if there are vibrations, it means that locally the structure is distorted, and this distortion will change the optical resonance frequency, just like in the Fabry-Perot cavity when the end mirror moves. Since everything is confined to such a small length scale, namely on the wavelength of light, the coupling turns out to be really gigantic because everything has such a strong mode overlap. And then, taking this as a starting point, it's not hard to imagine that now you can go ahead and design more complex circuits or arrays. For example, here a periodic arrangement of such defect modes, each of which carrying an optical and a mechanical mode, and they would talk to each other simply because they sit so close to each other. So if I want to describe this theoretically, I would say that each of the unit cells would be a standard optomechanical system of the sort that I already described to you. So I have an optical mode, a mechanical mode, and an interaction between them. Maybe I also drive the optical mode with a laser. Yeah? So that is the same kind of optomechanical system repeated again and again. Here's a slight technical detail. What we really care about is not so much the absolute frequency of the cavity or the absolute frequency of the laser, but really the distance between the two. Because it turns out when this distance matches the mechanical frequency, that is when you get the kind of photon-phonon conversion process that I was talking about. So these are the individual unit cells. However, what you want to look at as well is the coupling between neighboring cells. So if a photon hops to the neighboring site, and that is described here, AJ destroys a photon on site J, AI dagger would recreate the photon on a neighboring site. So before we go and employ this kind of structure and see what it can give us, let us take a step back and ask what this all means from a more general point of view. Because what you get here is really, I would call it a light tunable metamaterial for photons and phonons. It is light tunable in the sense that the laser determines this laser enhanced coupling constant G that will operate on each of these optomechanical systems that you've coupled together into an array. That also means that you get a tunable band structure. This is a periodic array. You will get, as I explain in the following in more detail, a band structure of photons and phonons, and you can tune this by the illuminating laser radiation. Okay, so now in order to demonstrate one of the interesting things that you can do on the basis of this, I will have a brief interlude telling you something about topological transport. And to go there, let us imagine the following situation. Here you have a piece of material and you hit it with a hammer at some point. What will usually happen is that a sound wave will spread out from this point into all directions until it fades away. However, for certain applications, it would be really nice if we could force this sound wave to propagate not just anywhere, but only in a well-defined one-dimensional channel. And it would be even better if this one-dimensional channel were unidirectional. Unidirectional in the sense it only goes to the right and doesn't want to go back to the left. If that is the case, it turns out that then if it hits a corner, it cannot decide to be reflected back, but it has to follow the boundary of the sample, as it were, to snake around the boundary. And this will be true even if the boundary is slightly distorted. So we call these waveguides, these unidirectional waveguides, chiral edged states. Now this is all really part of a field called topological materials. And so to introduce you to that, I first want to remind everyone, why do we like topological properties? We like topological properties because they are very robust and very generic, by definition, because topological properties are those that you don't break by smooth deformations. So for example, if you take this Möbius strip and you deform it smoothly without ever cutting it, then it will forever remain a Möbius strip and never turn into a normal strip. And so whenever you encounter a topological property in physics, you know that it will be very robust and very generic and therefore of general importance. This was also honored by last year's Nobel Prize to these three gentlemen for their theoretical discoveries of topological phase transitions and topological phases of matter. Now, on the mathematical level, what do we have? What is the core of the description? Well, look at this Möbius strip at first. In order to describe it mathematically, you would say, I pick a coordinate system on the surface, and I have a mapping from this coordinate system to a three-dimensional space to describe the shape that I'm trying to describe. And then I'm looking at all possible continuous smooth deformations of this function R of u, and they all form a large class of objects that look different in detail but have the same topological properties. Now we can transfer this to the world of quantum physics. For example, look at a periodic lattice like a crystal and look at the Bloch wave functions that we have. So as a function of wave vector, we get a wave function that describes propagation in this periodic lattice. For each different k, we get a different wave function. And so this will now take the role of this map R of u. Instead of that, we have psi of k. So we want to describe the topological properties of these mappings from k space to the space of wave functions. And to make this more concrete, let me pick the simplest possible lattice, a two-dimensional square lattice. But to make it slightly more interesting, really per unit cell there are two orbitals, the green one and the blue one. And so an excitation like an electron or maybe a photon can hop from site to site. And in order to describe its wave functions, so the solutions, say, of the time-independent Schrödinger equation, we would have always e to the ikr because this is a periodic structure. However, since there are two orbitals, I also have to tell you what is the amplitude to be on the green side or on the blue side. So these are two amplitudes that also depend on k. And now I want to go ahead and somehow visualize this because I anticipate we see interesting topological properties of these wave functions. How do I visualize a two-level system? Well, I remind myself that this is something like a spin 1/2. And a spin 1/2, I can always visualize the wave function by drawing the Bloch vector that simply tells me which way the spin is pointing. So for each k, I will have a different spin direction, and that is my way of visualizing the wave functions. And so now I can go ahead and do this. Depending on the microscopic details, I might get something that rather looks boring. All these spins are more or less pointing down, nothing very interesting. Nevertheless, if I change the microscopic parameters of this model, what I can achieve is a vastly more interesting situation where you see something like a vortex, or the experts would call it a skyrmion, has appeared in this picture. And even without knowing the details of mathematics, if I tell you that these Bloch vectors are always unit vectors, you can sort of believe me that there is no smooth deformation that takes this vector field back into the trivial vector field. You simply have created something like a knot. Now, mathematicians have a way of calculating this instead of just looking at the picture, and you can take a certain integral over gradients of the wave functions, which will give you an integer number that will have different values depending on whether you have this vortex or whether you don't have the vortex. And that number, that interesting number, is called the Chern number. It is an integer, and therefore it is topologically robust. Because as you change smoothly microscopic parameters, you can imagine what can happen to an integer. Mostly it will stay constant until at very special situations it will jump. This is all that can happen to an integer as a function of a continuous parameter. Okay, so this is already interesting. But there is another interest in these Chern numbers, and that is what we call the bulk boundary correspondence. So they tell us something about what happens at the edge of a sample or at an interface. Imagine that you have two pieces of this microscopic material that happen to have different Chern numbers, here 0 and there 1. Then it turns out if you look at a frequency inside the band gap or an energy in the band gap, there will be no states here and there will be no states there. You're in the band gap. But it turns out that at the interface, you're guaranteed to have a state. And it turns out the number of such edge channels can be counted depending on the difference of these Chern numbers. Furthermore, it turns out that these edge channels are chiral, so they only go one way, and that means they are robust to disorder. So if you deform things microscopically, they still go only one way. Okay. So now, after it had been understood that the quantum Hall effect is tied to the Chern number, which is then tied to the electrical conductance, people also understood more recently that there is an array of materials called topological insulators, where you don't even need an external magnetic field, but where spin-orbit interactions are good enough. And since then, it was obvious to ask, if this is so interesting for electrons, how can we see the same kind of physics in different systems, for example, cold atoms or photons or magnons? Now, here I will be telling you something about how to implement such ideas for phonons using light. And that is work really done by my PhD student Christian and by my former postdoc Vittorio Piano, who has now taken a faculty position at the University of Malta. So to prepare this story, if we want to have topological transport of phonons, of sound waves, of vibrations, what is the important microscopic ingredient? There's something that I didn't yet tell you, that I needed to go from the trivial case to the interesting case. And that is that if you look at it microscopically, the hopping amplitudes that take your excitation from one to another orbital, they must contain some non-trivial phase factors. Otherwise, nothing interesting will happen. Now, for an electron, that's quite easy. These are the phase factors that you get as Aharonov-Bohm phases if you're subject to a magnetic field. Or these are also phase factors that you get when you have spin-orbit coupling. But obviously, vibrations neither have a charge, so they don't feel a magnetic field, nor do they have spin-orbit coupling in the standard way. So we need some new tricks. The earliest proposal to have topological transport of sound waves is really from the area of biophysics, because in this publication, there was speculation that in so-called microtubules that make up your cell skeleton, there might be topological sound waves if the individual building blocks of these microtubules are somehow magnetic, so there will be some magnetic interaction between them. This is at the moment still a speculation, but this is really the first example of where people thought about topological transport of phonons, and until we looked into it, it was actually the only example. Now we set out to have a way to design topological transport of sound waves, and of course using optomechanics, using the light field. And it turns out that in the end, if you do it right, the ingredients required for that are fairly simple. You just need a suitably patterned dielectric, like the one shown here, and a suitably patterned wavefront for your laser beam. Now, in order to understand this, here's, so to speak, the crucial building block that we will build our lattice out of. Again, in a cartoon picture, the yellow circles are phonon modes, the blue circles are photon modes. And then you can have hopping of phonons and hopping of photons, but you can also have interconversion, phonons going to photons. So a phonon could decide to be converted to a photon, then the photon could jump to a neighboring site, and the photon could be back converted into a phonon. And this will all happen with an amplitude G that is set by the laser intensity, by the laser amplitude. And as I told you before, this amplitude can be complex. It can have a phase. And there you see the phase that we will make use of. This is the kind of phase that for electrons you would get from the Aharonov-Bohm effect in a magnetic field. For phonons here, we are using the optomechanical interaction. Now, in order to extend this to a lattice, here's a unit cell of the lattice. The easiest way to do these things is to have a 3-site unit cell, simply because 3 sites is the minimum you need in order to distinguish between clockwise and counterclockwise motion. So you have 3 sites, and they are illuminated by lasers, or by one and the same laser, but a different phase on each of the 3 sites. And the simplest, most symmetric configuration would be to have 120-degree phase difference, and then you can implement a kind of clockwise or counterclockwise circulation of the phases. If you wonder how this looks like, if you extend it to a lattice, it would look like this. So what I'm showing you is, as a rainbow color scale, the phase pattern that you will need if you want to build a lattice out of it. And then the idea would be to place the sites of your optomechanical defect lattice just here, triangularly around such a phase singularity which sits in the center. So the phase winds up by 2 pi if you go around this phase singularity. It turns out this is rather easy to get, and that's a nice textbook exercise for all the students. If you take 3 plane waves superimposed at angles of 120 degrees between the plane waves, and you plot not the intensity pattern but the phase pattern, this is what you get. So you automatically get the right pattern. And then that would mean we have an optomechanical array with localized optical and mechanical modes illuminated by such a laser pattern and feeling these different laser phases. Now this is a periodic arrangement of photons and phonons. I can go ahead and calculate a band structure like for any periodic lattice. And if I calculate this band structure, in total it will have 6 bands, simply because in the unit cell there are 3 photon modes and 3 phonon modes, so that makes 6 degrees of freedom, as it were. These bands are looking quite familiar to anyone who has ever calculated the band structure of a Kagome lattice, which is this lattice. However, if you zoom in, you get bands that are predominantly of mechanical nature, and these already have band gaps that have opened up because of the optomechanical interaction. That's already interesting. It's an effect of the optomechanical interaction. But in order to tell whether that is topological, it's not enough to look at the frequency versus wave vector. Yeah? So in order to tell whether a band structure is topologically non-trivial, you always have to look at the wave functions. Remember psi of k. And in order to quantify these things, you want to calculate the Chern numbers. So if you calculate the Chern numbers for this particular configuration, what you find out, they are not 0. They are different from 0. So this is topologically non-trivial. And then you can ask, how do they depend on laser frequency or laser amplitude, which are the experimental control knobs, and you get a rather rich phase diagram as shown here. But the important point is these Chern numbers are not 0. Thank you. And so you can go ahead and ask yourself in a simulation here, what happens if I excite sound waves locally? Then they will actually, it turns out, as anticipated, snake around the boundary of the sample. So truly you form these chiral edge states by these optomechanical tricks that you played on the structure. And so what do we gain here? Well, this would be an example of fully optically controlled topological transport of sound waves. And because it's optically controlled, you can also in principle form arbitrary domains by shaping your laser pattern, and you can even switch things in a time-dependent fashion because everything is controlled by the laser drive. To put this into context, after we brought out our proposal, there was a number of groups that implemented on a macroscopic level topological transport of vibrations. Here you see coupled pendula or coupled gyroscopes. This is already very nice, but these, of course, are proof of principle experiments. There is no known application on the macroscopic scale. So in order to really have applications such as for building quantum networks for phonons with robust chiral edge states, you really want to go to the nanoscale, and this is what this would be good for. And so there is actually a first attempt at an implementation of this structure. This is the optomechanical Kagome array fabricated in the lab of Oskar Painter, with whom we collaborate. At the red circles, you would have localized optical and mechanical modes. This particular structure does not yet work simply because the fabrication disorder is still too large, so the optical modes are still shifted too much in their frequencies and don't really talk to each other. But there are ways already how to engineer this in the future in order to improve the situation and really get to where we want to be. And so maybe finally, can we turn this around? I've talked about how to use the optomechanical interaction in order to create a tunable topological transport of phonons. Can we also have tunable transport of this sort for photons? And the answer is yes, and actually you can practically use the same unit cell, only now you read it slightly differently. You say that I'm injecting photons, and sometimes a photon gets converted into a phonon and then gets back converted into a photon and picks up a phase while doing so. And then you have this unit cell and you pick up a kind of Aronoff-Bohm phase. And from the point of view of a photon, this will now look like an artificial magnetic field, yeah, like the Aronoff-Bohm phases. And so, for example, if you were to plot the kind of energy or frequency diagram, photon frequency versus this artificial magnetic flux, you see the famous Hofstadter butterfly spectrum that was first investigated for electrons hopping around on a lattice subject to a magnetic field. And it turns out the lattice version of this has not yet been implemented, but the most simple unit cell has been implemented very recently, again in the lab of Oskar Painter. Here you see an optical and a mechanical mode in the left-hand cavity, and the same structure, optical and mechanical mode, in the right-hand cavity. They are coupled by a waveguide that can carry both photons, that would be this link here, and phonons, that would be the other link down there. And since they are driven by lasers with different optical phases, you really get this situation, and you get an artificial magnetic flux. And then if you shine photons from, say, the left, and then they are transported to the right, they will experience a different phase as if going the other way. And if you add some dissipation, actually having this new situation not only gives you a different phase, but even gives you different intensity for the transport from left to right or right to left. Okay, so that was all I wanted to tell you about. Let me skip the few further remarks that I had on purely phononic implementations and rather go to the end of my presentation. What I hope I have convinced you of is that you can really design topological transport or transport more generally for phonons and photons using optomechanics in order to break the time reversal symmetry with such a pattern of optical vortices. And first experiments are underway. As an outlook, I want to mention that in all these situations, these setups still work in the same way classically as they would work on the quantum level. So there's no difference because everything is linear in the end. However, if you go to the quantum regime, you may be interested in how quantum noise is transported or modified by these measures, and how then the bosonic nature of the excitations of the phonons or the photons can become crucial. And it will become crucial once you have nonlinear situations. Think of a nonlinear optical medium in which such processes take place, or you have an anharmonic phononic crystal in which such processes take place. And then you can, on the simplest level, really have, you can pump your nonlinearity, and you can have processes where you create two photons or phonons at the same time. And as you are working in optics know very well, that can create an optical parametric oscillator, and it can create amplification. So here, if you combine this with such topological transport, you can have a situation where you inject a small signal at one point, and then it is transported along a chiral edge state where it will never be backscattered, so it's robust against a disorder, and at the same time it will be amplified, only then to be ejected out of the system and then maybe being fed into some further amplifier stage. And the beautiful point about this is any noise that is at these further stages will never come back to your signal source, simply because everything is non-reciprocal. Okay, so with that, I'm really at the end of my presentation. These are just a few references. Thank you.
Great talk. I was intrigued by your analogy, or maybe it was more than an analogy, which is my question about the optomechanical coupling and the Raman effect. So if I take your suggestion seriously, then I'd say, well, let me think about the molecular version where I need not only the frequency difference matches, but I need also that there is a coordinate dependence to the polarizability. So I would imagine in your coupling term that there must be somewhere contained in there a term which has to do with the first derivative of the displacement. And that this, then my question would be, what would be maximizing that coefficient of that first derivative? And can I think of it in this way?
effectively, this is actually what happens. So I didn't show it in this way, but you would have your cavity frequency as a function of position, and it's the first derivative of the cavity frequency with respect to position that will provide my coupling strength. And if you ask me how to optimize it, it sort of already became apparent in the Fabry-Perot simple example. You want to make the overall size of the structure as small as possible, because what really enters in the end will be the ratio between the mechanical 0-point fluctuations and the overall size of your optical cavity. And so you want to improve this. It's also very interesting that you mention it. Very recently, so to speak, the concepts of cavity optomechanics have been taken back to, let's say, to the field of molecules and Raman scattering and cavity-enhanced Raman scattering. And it seems that a few unexplained, say, if you look into surface-enhanced Raman scattering, there was for a long time a kind of puzzle that the signals were sometimes quite a bit larger than you would expect, even by orders of magnitude. And there is some speculation that this may have to do with some of the effects that people have understood first in the field of cavity optomechanics, that if you drive with a Blue detuned laser, you can actually have self-induced oscillations in these structures. And there are first experiments actually to test this interesting connection between cavity optomechanics and Raman scattering of molecules.
In the first part, you started with the Schrödinger cat and Schrödinger mirror. So I'm sure that you know and you are aware of this sort of discussion. The analogus that you have, it is totally quantum, while the concept of Schrödinger cat is just linking a quantum word to a classical word which you don't have a coherence. So since the description that you have, it is fully quantum, I wouldn't call it really Schrödinger cat. I don't call it even Schrödinger mirror.
Well, so the point of view of Schrödinger was, let's take quantum mechanics serious and let's pretend for a moment that it applies as well to the microscopic object, that is the light quantum, as to the macroscopic object, that is the mirror or then the cat. And then he comes to certain conclusions that he finds kind of ridiculous. And at the time, his philosophy was to say, look, the conclusions are so ridiculous that apparently we have not yet understood something very deep about quantum mechanics. But nowadays, the attitude is a little bit different. One takes this as an inspiration and says, again, together with Schrödinger, says, let's assume quantum mechanics is valid at all scales as a first working hypothesis. And let's see in the lab how far we can really push this. And maybe at some point it will break down for some reasons that we don't yet understand. But the simplest reason would be that there is some fundamental source of decoherence that scales with the mass of the objects that you cannot easily see for the microscopic objects, but that would be there. So I think it's a good working hypothesis to start with a quantum description, because then at least you have a prediction and then you can see where it fails. So that's the attitude.
I have a question regarding to the relation to broken time reversal symmetry. So normally, if you're not in the high energy physics regime, there's time reversal symmetry. And when in, for example, solid state physics, you read about broken time reversal symmetry, usually a magnetic field is involved, which is not turned around when you, but deep inside we know magnetic fields are produced by currents, and if you take these currents around, then everything is time reversal symmetric. So when you say here it's just the geometry that does this, how do you save time reversal symmetry in the real deep sense?
Yeah, okay. Now what happens here is really very close to the situation you mentioned. In solid state physics, we keep an external magnetic field and we don't turn it around. We keep it fixed, and that's how we externally break time reversal symmetry for the solid state object. And here really the same happens by the laser drive. So if you see this pattern of optical vortices, you could of course choose to turn around this phase pattern, and then everything would actually also work the other way. So the phase pattern that you produce in the laser, that's what breaks your time reversal symmetry. That's really like the magnetic field.